Hi chemists, today we're going to be discussing bond energies, or bond enthalpies, which is the energy required to break a specific bond in 1 mole of gas. Delta H is equal to the bond energies of the bonds broken minus the bonds formed. So this idea is combining our thermodynamics unit with our Lewis dot structures unit, because in order to calculate the enthalpy, or the delta H, you need to know what bonds are broken and what bonds are formed. So we're going to be drawing Lewis dot structures in order to determine what bonds make up the molecules. Now keep in mind that it takes energy to break a bond, so that is positive energy, and energy is released when a bond is formed, so that energy is negative. And this negative sign here, or this minus sign, takes into account that energy is released when a bond is formed. So when you're doing the math, you're just adding up the bonds broken and then subtracting all the bonds that are formed. Here is the table of average bond enthalpies. The unit here is kilojoules per mole. So notice this table is divided into single bonds and multiple bonds, meaning double bonds or triple bonds. So for example, it takes 413 kilojoules to break 1 mole of C to H bonds. So you can see the bond and the average bond enthalpy to the right of it. This table is included in at the top of your homework sheet, so you will have this table, and I will give you the necessary information from this table on a quiz or a test so that you have the average bond enthalpies for specific bonds. So please note that you do not have to memorize any of this information. This table will always be given to you. Another thing to note is that here where it says O2, you should know the Lewis dot structure of O2 is O double bonded to O, so keep in mind if you're looking for an O double bonded to an O, that is 495 kilojoules per mole is the average bond enthalpy. Please note that these are averages, so when you calculate the bond energy using the average bond enthalpies, you're calculating an average or an estimation. That is because, in a way, not all C to H bonds, for example, are made equally, meaning that not all of the C to H single bonds, I'm just choosing this bond to discuss in particular, not all of the C to H single bonds are the same in all organic compounds. So the energy to break one C to H bond is not always going to be exactly 413 kilojoules per mole of bond. That number could vary a little bit depending on how many other bonds in the molecule have already been broken, or depending on what other atoms are nearby and bonded to that carbon or nearby carbons. So for polyatomic molecules, which are molecules that have more than 2 different atoms, these numbers can actually vary slightly, which is why you'll note here that the table says average bond enthalpies. So when we calculate the enthalpy, we again will be calculating averages. So let's dive into an example, and you'll note that on the bottom here I actually have the table, so we'll blow this up when we need it, but I'll keep it in the bottom for now. And this is one of the problems actually on your homework sheet. It's problem number 4, and we're going to do the part of the problem where it says find the enthalpy, the delta H, using bond energies, or bond enthalpies. So we're going to do that for this problem. H2 gas plus C2H4 gas yields C2H6 gas. And I'll show you how I do that. I have a very specific way of writing it that I think is helpful for me. And again, you can adopt this method. So I am going to write 1 to start with. Please note that that 1 comes from the fact that there's 1 mole of H2. And then I'm going to draw parentheses, and I'm going to say plus another 1. Notice this equation is balanced. I should have mentioned that. This is already balanced. So that 1 comes from the fact that there's one C2H4 molecule here, or 1 mole of C2H4 gas. And I'll draw a big parentheses here, and then an arrow, and then another 1 and a big parentheses. And again, this final 1 comes from the 1 C2H6. Now inside these big parentheses, I'm going to draw the Lewis dot structure. So for H2, it looks like that. For C2H4, it looks like this. That's C2H4, and for C2H6, it looks like this. Please note that lone pairs do not affect your bond enthalpies because there is, if you look back to our table here, lone pairs are not part of a bond enthalpy. We're talking about breaking and forming bonds, so lone pairs do not participate in bonding. However, I highly recommend you draw lone pairs in your Lewis dot structures because they can help you get the structure correct. I may not have known that this was a double bond had I not thought about total valence electrons, and therefore I made a double bond rather than having lone pairs on those carbons. So I highly recommend, just like we have been using lone pairs in our Lewis structures, keep putting those in to help make sure you get the Lewis structure correct. Now diving into the math, delta H is equal to bonds broken minus the bonds formed. And now we're going to add up the bond enthalpies. So here's how I write it. You want to think about all of the bonds that are broken are all the bonds on the left side of the arrow, and all of the bonds that are formed are the bonds on the right side of the arrow. Now in terms of what bonds are actually broken and formed, not all of the bonds are actually broken. For example, this C to H bond isn't going to break. But we will, if you don't know the mechanism of the reaction, which you might not, you'll get this problem correct if you break all of the bonds in the reactants and form all of the bonds in the products. Therefore, the net bonds broken and formed will be accurate if you just break all of them and form all of them in your math. So delta H equals bonds broken. We have one H to H bond. That's this bond that we break, plus 1 C double bonded to C. It's important to have that double bond. That's this one. Plus 4, 1, 2, 3, 4 C to H or H to C bonds. I'm going to make that a little bit smaller. Okay. Minus all the bonds formed. We have 1 C single bonded to C. That's this bond. And then we have 1, 2, 3, 4, 5, 6 C single bonded to H. Those are the bonds that we have that are formed. So again, it was bonds broken, which we break all of these, minus bonds formed, we form all of these. Now I'm just going to go through and from my table, which I'll blow up here, I'm going to put in the numbers. So for H to H on the table, it says 436. I'll write that below it. That's H to H. C double bonded to C is down here. Oops. That was 614. C single bonded to H was 413. I'll write that again over here. 413, and C single bonded to C is 348. And again, if you look at your homework sheet, you can have that in front of you to see the average bond enthalpy table. Now when you calculate the final delta H, keep in mind order of operations. So I'm going to do 1 times 436 plus 1 times 614 plus 4 times 413. I'm going to do that math, and then I'm going to subtract, in parentheses, 1 times 348 plus 6 times 413. I highly recommend doing the parts in the brackets first and then doing the subtraction at the end. And when you do the math, you should get negative 124 kilojoules per mole. Because delta H is negative, this reaction is exothermic, meaning that the bonds formed by the products are stronger than the bonds broken in the reactants. Alright, chemists, let's do one more example. So this is number 3 on your homework sheet, if you have that pulled up. And it's N2 gas plus 3H2 gas yields 2 NH3 gas. Notice that this is already balanced for you. So you're finding the delta H using the bond energies or bond enthalpies. So we're going to start by writing down our equation. Delta H is bonds broken minus bonds formed. Okay, and we're going to draw the Lewis dot structures. So notice my coefficients are going to be different for this problem. For N2, we have a 1, but for H2, there are 3 H2s. Notice that from our balanced equation, and we have 2 NH3s. So again, these coefficients come from the stoichiometric coefficients in your balanced equation. Then I'm going to draw the Lewis dot structures in my big parentheses here. This might take you a little bit longer than it takes me. Feel free to pause the video to do so. And then ammonia or NH3. Notice, like I said before, I am including my lone pairs, not because it changes how I do the math, but because it's important in terms of creating octets to get those Lewis structures correct, so you know particularly what types of bonds you have, double, triple, or single bonds. So in order to calculate the delta H, again, we're doing bonds broken minus bonds formed. So we're breaking all of the bonds in the reactants, and we're forming all of the bonds in the products. So one of the bonds we're going to break is N triple bonded to N, and we have one of those. And we're also going to break 3 H single bonded to H. So those are the bonds we break in our reactants, minus the bonds formed in our products. Notice that we have 1, 2, 3 N to H bonds inside the parentheses, but times 2 makes 6 N to H bonds total. Now we go to our table. N triple bonded to N, down towards the bottom is 941. I'll put that in a different color. There we go. 3 H to H. H to H is 436. And 6 N to H. N to H up there, 391. So now we're going to do the math. Again, think about your order of operations. I will do 1 times 941 plus 3 times 436 minus parentheses 6 times 391. And when you do that math, you should get a delta H of negative 97 kilojoules per mole, also exothermic. So you're forming more stable products with stronger bonds.